Namaskar, welcome back. So this was the last slide where we stopped discussing about the colluvial wedges seen in reverse faulting environment or compressional tectonic environment. And as we have discussed this part in uh, normal faulting environment also, that number of colluvial wedge will be indicating you respective individual earthquake. So if you have two colluvial wedges, then you can say that there were two earthquakes along that fault. Now, the Japanese literature, this type of structure has been referred as a D structure. Okay, and the reason is very simple, that it it is something like, the shape is something like D here, so that they call this as a D structure. Let's move further and see what we can get an indication if we are having multiple colluvial wedges, and this is again a schematic diagram which shows that how uh, the faulting occurred, and then after faulting the degradation of the scarp which resulted into the deposition of the colluvial wedge, and over the time then another event took place, and so on. Now the criteria which we looked in or we discussed in the normal faulting environment, here also it remains the same, that you have to be carefully look at the surface inclination, that is the angle of the surface, that maybe we can say the slope of the surface. So what is the amount of slope of the surface, and as we have discussed in one of the slide, that the colluvial wedges, how we can distinguish between the normal sedimentary faces and the colluvial wedge material, that it will be but disoriented sections of soil fallen from the upper part of the slope, or you can say the hanging portion of the scarp, and also it will be more fragile as compared to the surrounding ones. So similar process has been also considered here. So if you see one, that is your A, then that shows that there was a surface which is dipping or having a slope of around 6 degrees, and then resulted in the faulting. Okay, and faulting which definitely was because it shows higher angle, so it is in reverse fault. Then after the formation of the scarp during an earthquake, the B, it shows that there was an erosion of this portion of the scarp, and then what you see is the deposition of the colluvial material. And finally, as we discussed in the scarp degradation, the scarp will get stabilized as it reaches the its angle of repose. Okay, so at 25 degree it stabilized, and again another part which we discussed in the previous lecture was that you will see a sort of an debris first, and then you will have the finer deposits. Okay, so we can say this as an wash faces, and this is debris faces. So we will see a sort of an fining upward sequence. So this we should keep in mind when we are looking for the colluvial deposits. Now again, after this whole slope has been stabilized, and what we see is the soil which has been forming here, but the previous soil is sitting over here. Okay, so this is the previous soil unit which is again, this is an hanging foot wall. This will be your foot wall, and this will be your hanging wall. Okay, so the slope of this older soil is different than this one. Okay, slightly it will be different because it is having the same, but in case of like in the footwall side, we'll see that there is some sort of an variation. Now second event occurs. So this was event 1, and then after the slope, scarp slope was stabilized, stabilization of the scarp slope. So after the scarp face was stabilized, there was another event, and that was event 2, and this event 2 displaces this soil, okay, as well as the colluvial wedge. So we can say that this was colluvial wedge 1, for example. Then, so this was been displaced actually. Now again the same process will operate in terms of the erosion. So this, and F, you have erosion plus deposition of colluvial wedge 2. So this is what we are seeing is the deposition of the colluvial wedge 2. And similar process will take place, and then you have the finer deposits. And what we see is that still the slope is higher. So final slope will stabilize at around 25 degrees. So again what we see is that you have the finer deposits which started from here, but it will end at this, and then you have the, which will also represent your surface, okay, the newer surface. So what we have, if we see the section, for example, when we do the paleoseismology, then we try to open this whole portion, okay. So then you see the debris, disoriented fragments of the debris over here, and then finer deposits, okay. So this was the surface 1, okay, and then we have another colluvial wedge. So this is your, you can say this one is your colluvial wedge 1, okay, and this is your colluvial wedge 2. So if you come across such type of indication, then at least you can say that there were 2 events, okay. So this is how we are going to identify the based on the colluvial wedges also, and of course as I discussed in one of the lecture, that we can also uh, you know, identify the number of events based on the cross-cutting relationship. So for detail what we have discussed, you can also refer this legend which has been given, that you have the wash elements, that what we were talking about here. So this is again the finer one is your wash deposits. The wash facies deposits is there, and then the coarser one is your debris flow or the debris element. So anyway, we'll come to this section later also, but this is basically what we do, that after having detailed investigations, we try to put the faults and try to identify different litho units, okay. This we will discuss in the coming few slides, okay. So let's move further ahead. So again, in this trench, if you see, then we have at least 2 colluvial wedges. So colluvial 2 is the older one which was displaced during the latest event, and then you have the colluvial 1 that was deposited after the even this has also been displaced actually, okay, because this is colluvial 1 which you see is also been displaced over here. So because the fault which has been shown here is this one, you have a fault over here, okay, which goes like this, and then you have this one, okay. So even the colluvial 1 is been displaced, okay, and colluvial 2 is also displaced here, So that, or you can say that if this fault is not extending, but it seems to be extending further up over here, it goes like that. Okay, so this was after the colluvial wedge 1. Okay, but at least you can say that minimum 2 earthquakes were uh, in this. Okay, so event, if we say that this was the older event, so this colluvial was formed at that time, and then another event, this colluvial was been deposited, and then final displacement was during the event 3. Okay, so this is how they have identified that more than 2 earthquakes have been triggered here. So that is again on the basis of the soil formations. Okay, so you can also say that looking to the soil units. Okay, because one thing that the interval between any event, say event 1 and event 2, will not be very short. Okay, will not be short. Okay, a shorter time span. So the period between this two events will result into the soil formation process. Okay, or will result into the soil formation. So that those soils have been identified over here, and that they said that because this colluvial was also been displaced. Okay, so has to be more than two events actually, at least. Okay, so in this another um, like important point has been shown is that sometime you may not come across the comparable sequence on either side. Okay, let's say that we have different units. Okay, and when they are displaced or deformed, then we expect that they will be seen somewhere over here also. Okay, on the other side of the wall. Okay, so but in this case of the trench, we will you don't see any comparable unit on the footwall side. Okay, when you are comparing the lithostratigraphy exposed on the uh, hanging wall side. So this is your hanging wall, and then this side is your footwall. So no similarity was been observed on either side of the fault plane. Okay, only based on only the borehole data suggests maximum displacement of the fluvial cobbles. Okay, so with the help of the boreholes, the fluvial cobbles, they were able to see that they were showing maximum displacement, and the fluvial cobbles or the fluvial material or the gravelly unit, what they were able to see at this level. Okay, this unit is sitting over here. Okay, so net displacement, if we see with compared to this layer, is much larger. Okay, as compared to what we see in this portion of the trench. Okay, so this is the exposed section, you can say. Okay, so in an exposed section, you are unable to pinpoint that what is the amount of displacement, but borehole helped them in understanding that the displacement was far greater than what they see in the trench, because the the displacement which has been seen in the trench could be related to the younger events. Okay, and a unit, gravelly unit, that is fluvial cobbles, that unit was displaced multiple times during each earthquake, okay, or during each individual earthquake. So in this, at least four uh, events have been identified, but only two wedges are seen over here. Okay, so two wedges are faulted and two soil units are faulted. So based on this, they have identified that there is at least four earthquakes uh, along this fault. Okay, and of course the displacement which has been observed based on the your depth of the pebble in the footwall side, that also indicated that amount of displacement was much higher. Okay, now let's see a couple of example uh, of deformation pattern which was been observed during this uh, Alasnam earthquake. Okay. So this presentation I got from Professor Mustafa McGroy, who is one of the finest and renowned paleoseismologists in from France, but he, of course, around in world he is one of the finest and renowned paleoseismologists. So he did a lot of work in this area of Lasam earthquake. So let's see about what exactly we uh, have the examples or the field evidence of this Al-Atsnam earthquake. So this is from Algeria. Algeria is located in the South American plate on the northwestern side over here. Okay. So this is the portion, and this is usually getting affected by the strike slip faults and the thrust faults. Okay, so deformation between these two region is almost like uh, at the rate of 4 to 6 millimeter per year. Okay, and also clearly indicated by the occurrence of earthquakes during the historic time, ranging from 5 to around 6 or 7 magnitude earthquakes were been seen here. Okay. Now, this is the Landsat image of the area, uh, date back to 1977. Okay. And what they observed was quite interesting, that even though the deformation, ongoing deformation is like you have almost the vectors are like this, okay, where the two plates are uh, interacting with one another. But once the strike of, for example, if you have a strike like this of the fault and then goes like that and then goes up, okay, and then you have a vector here which is the plate motion, okay, vector, then the deformation here will be mostly, you will see a thrust faulting environment. Okay, so you will see a thrust faulting environment, but so there's the thrust, but here you may see a sort of an uh, a strike slip. Okay, so that will be the difference. Okay, so again, so you will see a strike slip motion along this, because it is not exactly perpendicular to the or normal to the your uh, motion, plate motion. Okay, vector of the plate motion. So they were able to pick up different segments which has been shown here. Okay, so segment 1, segment B, A, B and C. Okay, so if you look at from here to here, the strike is different, and then on other side the strike is also different over here. Okay, and strike over here is different, and then you come down here, it is like this. Okay, So they were able to see that in different segments, uh, they observed a different pattern of deformation, but overall deformation was on a thrust fault. Okay. So this was uh, the earthquake of Alasnam, and magnitude was 7.3. Now, interesting landform change, or you can say that uh, locally it affected the drainage and resulted into the different change in the environment. Okay, so that got affected. So this is a sketch which shows uh, that how this one of the major river which used to flow through or across the fault. Okay, so fault lies somewhere like it has been shown here. Okay, and how that was been blocked because of the uplift and resulted into the ponding conditions and all that for a longer period. So this is the deformation where uh, like in section you can see that it was a clear cut folding which was been observed during this Alasnam earthquake, and there was uh, a ponding here which was because of this uplift which blocked the channel for some time, but later the channel eroded the anticline. So this was in sort of an, you can say, warp form or the fold. Okay, typical of fold related fault related folding. Okay, so this was the direction of the Shelif River. Okay, so it flowed in this direction, and the deformation was, you can say that this side was, so if we say this is north and this is just arbitrary putting, so northern side moved up on the southern portion. Okay, and the it blocked this, resulted into the ponding. Okay, so this was a temporary ponding formed by an faulted anticline. Okay. So and this Shelif River so was been blocked for some time, but it eroded later on. So this was in 1980, the earthquake 7.3 magnitude, and the deformation pattern. And further, before we go to the further details of this, so the trench investigation of across this fault, it revealed that such ponding condition was formed, or they were able to see the uh, lake deposits. Okay, older lake deposits. So that clearly indicated that this type of process happened in the past, and the channel was also blocked in the past. Okay. So likewise, what we were looking at the colluvial wedges, one can also see that if the environment is getting affected locally because of faulting and because of the blocking of the river, it will result into the artificial or natural pond. Okay, temporary ponding is there. So ponding will give you a different type of deposits. Okay, laminated and deposits will be there, and then you have very fine deposits. So that sequence was been observed uh, subsurface. Okay, so that indicated there were similar type of events in the past also. Now coming to the change in the strike and relation with the deformation pattern. So what they were able to see that so this was the site, the close up which we were looking at was this one here. Okay, where the Shelif river was ponded, and then further it crossed the centric line. Okay, so geomorphologically and control of drainage system by Al-Islam. Okay. So this is what they identified in other areas also, that there was some sort of a deviation of the streams, and that was your Fuda river also, that got deviated because of this formation of the anticline. Usually, this concept we are going to discuss, that when what we called uh, fault propagation. So we usually talk about the lateral propagation. Okay, lateral fault propagation. So this is the propagation is along the strike. Okay, along strike propagation. So this can result into deflection or the deviation of the streams also. And we have, if I'm not wrong, we briefly discussed about the Bias channel, or this one example was we discussed, and second one was your Dabka river channel. So this is in Punjab Himalaya, and this one is in Kumaon Himalaya. So let's see further what sort of deformation they were able to see, and during this 1980 Al Aslam earthquake. So the deformation, the scarp runs somewhere over here. Okay, so this one is the scarp here, and they open up a couple of trenches across the scarp to understand the pattern of deformation, and they were also they saw that mainly two type of deformation they came across. One was along, I would say that high to low angle faulting. So you can say reverse faulting plus thrust faulting. So both this gets into your compressional tectonic environment. Now, at the same time, as I told that since there was change in the strike of the fault, the deformation pattern was different. Okay, and two examples of the photographs which have been shown from different areas, but during the same faulting or the same earthquake, it's typical of strike slip. Okay, so what you see here, that this block, so this is the line here which you can try to see boundary. Okay, so this block has moved like this, and this one has gone like this. Okay, so this is typical of what we can say as a left lateral. And here also, if you see, then you have this deflection of the rail track. Okay, where this portion has moved this side and this portion has moved. So left lateral strike slip was been observed in different segments. Okay, and this was clear cut a thrust fault scarp. So as we have discussed in the lip technique, that the amount of displacement is very much important. Okay, so in one of the slide in this lecture we were looking at that they also tried to see that what was the displacement of the sedimentary unit. Okay, subsurface. But on surface manifestation we also try to look at that what is the amount of displacement in terms of the vertical separation. So sometime that will help you in identifying at least the the scarp with the multiple events, or in field if you see a very high scarp, then you can also judge and infer that this scarp was not the product of a one single event but multiple events. Okay. So, this is what has been shown here, is that you have the 1 point or 1.1 to 1 to 1.5 meter of displacement during 1905. So, this was the scarp during 1980, sorry. So, and then uh, they also looked at that along with this displacement of uh, 1.5 to 2 meters, say, in number of places, the maximum displacement of the scarp was around 7 meters. Okay, so this indicated that this scarp is a cumulative scarp. Okay, so we'll stop here and we'll continue in the next lecture discussing more on uh, the deformational structures and reverse faulting, and we'll now see the examples from Indian side. Okay, thank you so much. Namaskar.